All right, guys, so some of you have taken chemistry or are taking chemistry and are going to start to see a lot of parallels between these functions that we keep using in class that are used for modeling exponential equations or logarithmic functions. They are also used in the real world a great deal, especially when we're dealing with things called exponential growth or exponential decay. So before I just give you a formula that's going to work to figure out exponential growth and decay type of scenarios, let's reason it out and let's see where this formula comes from. And I think you're going to start to understand where it comes from because we've done a lot of stuff like this in the past. So our first problem here says that James owns a chain of restaurants that operated 200 stores in the year 2000. The rate of increase is 10% annually. So that means that he's opening more stores every year at a 10% rate. How many stores does the restaurant operate in 2007? Okay, the first thing here is 10% could be written as a decimal, right? A percentage is a number out of 100. So 10% is 10 out of 100, which as a decimal could be written as 0.1. We're going to use the decimal version of these rates, especially when we're dealing with all these growth and decay problems. So let's just make a little table. We have the year, and we have the number of stores that he has. And so in the first year, the year 2000, we can start off here by saying that he has 200 stores. Pretty easy. Okay, in 2001, he still has those 200 stores. He's still got those. But he also added some more stores to that. So how many stores did he add? Well, the rate of increase is 10% of whatever amount of stores he already had. So how could I find 10% of 200? Well, I could do 200 times 10%, right? So what I'm going to say here is that he has 200 stores, plus he has 10% of those 200 stores. That's what he added. That's the increase of 10%, all right? And I'm sure we're all okay with that. This is the 200 stores he had the previous year, and then he added 10% of those stores as well. So we all know we could do 10% of that. We know he added 20 stores. Yeah, but I'm not really interested in how many stores that is right now. What I want to do is rearrange this so that it looks a little easier to deal with. And to do that, I'm going to factor by grouping. What is the GCF of these two terms? Well, I've got a 200 in each of those two terms, so I could factor a 200 out. And what would I be left with? Well, if I divide this first term by 200, I'm going to have a 1. And if I divide this term by 200, I'm going to have a 0.1. So I'm going to have a 1 plus a 0.1 left over. And we could simplify that even more. 1 plus 0.1 is 1.1. Okay, so what we've done here is we've figured out that in the year 2001, he has this many stores. So now we've got to remember that. Going into 2002, I'm going to continue to use red here. 2002, well, how many stores does he have at the beginning of 2002? He has this many stores. That's how many stores he has right now. But we know that over the course of this year, he's going to add 10% of that amount. Okay, so he's going to add 10% of that. And it starts to look a little confusing, but we remember that we can just use factoring by grouping here, pull out the GCF, which in this case is 200 times 1.1. I can remove that from each of these terms, right? I can take that out. I can take that out. What's it going to leave me with? It's going to leave me with a 1 plus a 0.1, which is 200 times 1.1 times 1.1. And we can do something even better here. We can push those two 1.1s together and call this 200 times 1.1 squared and make it real nice. So we've packaged this all up, and it looks like this. We are using our factoring by grouping skills to help us do that. So let's go on to the year 2003. In the year 2003, he starts the year with 200 times 1.1 squared stores. That's how many stores he has to start the year. But then James adds 10% of that to his number of stores because he continues to grow. So Let's factor this by grouping. My GCF is going to be that whole thing, the 200 times 1.1 squared. And what's left behind? Well, here, if I divide this by 200 times 1.1 squared, I get a 1. Here I get a 0.1. 1 plus 0.1 is 1.1. And I can package that up into 1.1 to the third. So hopefully you're starting to see a pattern develop here. And I want to point this pattern out to you. Let me use a highlighter. I'm going to grab green. So you'll notice that what keeps happening here is we keep getting an exponent outside of this 1.1, other than the first year. And there's a reason that that first year doesn't get that exponent and the other years do. Because technically, we could rewrite this as having that 1.1 to the 0 power, if I wanted to. And this one would be 1.1 to the first power. And there's your to the third. All right, so there is a pattern growing here. And the pattern comes from determining how many years it's been since the initial year. So we've got this other column that we could keep track of over here. This is the year 0, because in the year 0, that's our initial year. 1 year later, we end up with this expression 200 times 1.1 to the first. 2 years later, we end up with this expression 200 times 1.1 to the second. 3 years later, we end up with this expression 200 times 1.1 to the third, and so on. It's going to keep going, right? So this pattern will continue until the year 2007. And in the year 2007, we can see this pattern unfolding. It's safe to say that we're going to have 200 times 1.1, and how many years has it been since 2000? Well, it'll have been 7 years since then, so it'll be 1.1 to the 7th power. And that's where that exponent comes from, right? Okay. So, how could we have figured this out right from the very beginning? Well, there is a formula here. And if you ever get into a position on a test where you have to reason this out, you can do this. It's pretty easy to do if you're only going through 3 years. But realistically, I could ask how many stores will there be in 3010, right? And you'd need to have a formula for this because there's just no fast way to go about doing this in a table. So what we would do is we would use this exponential growth formula. Our exponential growth formula says that you have a total amount that is equal to the principal amount times 1 plus or minus, and that's depending on if we're growing or decaying, whatever the rate is, to the t power. So that's the formula. Let's write down what each of these variables mean one more time. So A is your total amount, and that's usually the future or the end amount. Not always. Sometimes we're dealing with a total amount and we want to know about the past. All right, but the P here stands for the principal amount, and that's usually the initial amount of money. 1 is constant. That'll always be there, and so will the plus or minus. But the R stands for the rate. For example, in this problem, we had a 10% rate of increase, and that rate has to be written as 0.1. If I had a 24% rate of increase, that would have to be written as 0.24. All right, so we're going to always turn whatever the rate is into a decimal if it's not already a decimal. And T is your time. And that's where these exponential functions come in, right? Because what we've got here, if we go back to our table, is I could determine the nth year, or to put it in terms that we've been dealing with, the x year, if I wanted to. That would be the year 2000 plus x. And I don't even have to know what year that is, but I could figure it out by just doing 200 times 1.1 to the x power, which is clearly an exponential function, right? So it's good that we've identified that we know how to deal with these exponential functions, because now we're going to start using them in these types of problems where we have real-world examples and we're trying to figure out how much money somebody's going to have, or how many stores there will be in a certain number of years. So in example B, what we're going to do here is we're just going to lay this thing out. We're not actually going to solve it, and we can solve it in class or you can solve it on your own. But let's just use our formula, we'll keep that in the frame here, to model this scenario. It says the attendance for a basketball game declined at a rate of 5%, and that's important. I already know the rate is 5%. I have to use 0.05 for R. Per game throughout a losing season, if there were 23,500 people at the first game, identify the exponential function that models the attendance of fans from game to game. I'm just going to call attendance A of G. We'll say G is games. Right, so G is the number of games. So I want to rewrite my function here, A of G, depending on how many games have been played. Well, my principal amount, the initial amount of fans, is 23,500. It says we're losing fans. So what we've got here is 1 minus, because we decide what sign to use based on if it's growth or if it's decay. So 1 minus, and that rate is 0.05. And the exponent is however much time has passed, and we don't know how much time has passed, so we're going to call it G. To simplify this, I would say A of G equals 23,500 times 0.95 to the G power. And you don't have to use G. You could use X. You could use T, whatever the variable is. But we want to know about games, so just to make it interesting, I'll use G for games. Okay, so just to highlight a couple things here, we've got our rate. I'll highlight this in blue. That shows up here. That's what that is. And our initial amount, which was the amount of people at the game, that's P. That's this 23,000. That's where that came from. Okay? And then these are the blue people. That's the rate. So you can see the connection happening there. If I were to say, okay, 23 games have gone by, how many fans are at the game? That's pretty easy to do now because I've got a function that tells me how many fans will be at any given game if I know what number game that is. Okay, so we're going to start using these functions, and we'll practice a little bit together in class tomorrow.